Welcome to my presentation for the ENC 2020. My name is Oliver Heirich and I'm from the DLR in Oberpfaffenhofen from the Institute of Communications and Navigations. I did this work together with my colleagues Benjamin Siebler, Stephan Andreas Lehner and Omar, Garcia, Crespillo. There are two main approaches for train localization. The first one is the state-of-the-art train localization that uses elements in the railway environment. The second one is the onboard train localization that uses elements exclusively on the train. This talk focuses on the onboard train localization. Before I start with the technical details, I want to motivate with railway applications that are enabled by onboard train localization. The first visionary application from DLR is called virtual coupling. Virtual coupling is a highly automated train separation that can operate below the braking distance. The two trains are not mechanically coupled, they are virtually coupled. The second visionary railway application is an autonomous train formation. You can see a self-powered cargo wagon that joins and forms a cargo train in a freight yard autonomously. Down to earth, we follow also applications and use cases for current railways. The first example is the safety overlay system ARCAS, the Railway Collision Avoidance System. In ARCAS, trains use onboard localization and exchange their locations via wireless communications. Each train analyzes the risk of possible collisions. ARCAS has been developed into market by a DLR spin-off and is operational at a German railway company. The second example is the end-of-train device. This device uses onboard train localization and is used for the monitoring of the train integrity. Track condition monitoring can be achieved with every train. This enables highly up-to-date information for the track infrastructure. The concept of the virtual balise is a way to extend the European Train Control System ETCS with onboard train localization based on multiple and exclusive trainside sensors. Virtual balise uses existing interfaces and replaces physical balises by location updates from an onboard train localization. An onboard train localization computes a track ID and a 1D position on the track. The main elements are measurements from onboard sensors, a digital track map, a localization algorithm, and for safe train localization, a navigation integrity method. The requirements depend on the application or use case. General requirements are highest availability in all environments and a track selective accuracy. The train location cannot be observed directly with measurements. It needs measurement methods in order to measure track features. The localization algorithm then computes the location from the measurements and from known track features of the digital track map. The questions are here: how can a measurement contribute to train localization? And what are useful measurement methods for train localization? So how can a measurement contribute to train localization? Let's start with a position on tracks. The first category is the train speed or relative over time category. This includes speed measurements, distance, travel distance over time, or its sum, the dead reckoning. The second category is the relative train localization that defines a distance on tracks between two positions. The third category is the absolute train localization with an absolute long track position, an absolute track identification, or a track identification at a switch. Let's have a closer look at the difference of absolute train localization and relative train localization. You can see here a train with sensors at each side. You can see the train end, the train front, and the train length. The absolute train localization determines absolute positions. An absolute position of the train end and an absolute position of the train front. In between there's a train length. The relative train localization determines the on-track distance between two positions, the train front and the train end. There is a direct distance between two sensors. The direct distance is always shorter than the on-track distance in curves. It is possible to compute the on-track distance from two absolute locations. It's also possible to compute an absolute location from another absolute location and the on-track distance. so absolute and relative train localization is connected. Robust and safe train localization uses confidence intervals and defines an occupied track. Therefore, redundant measurements are required and the navigation integrity monitoring. Navigation integrity methods compute protection levels based on a measurement analysis, failure detection and exclusion, and a sensor fusion monitoring. Confidence interval is the protection level in a long track direction. The navigation integrity guarantees that the true location is within the confidence interval, with a very low error probability. An application is safe when the confidence interval is smaller than a limit. The limit is defined by the application or use case requirements. Let's come to the measurement methods. We present measurement methods from 4 different types of onboard sensors: GNSS, IMU, magnetometer, and terrestrial radio ranging. This list is not considered to be complete. There are also other sensors. Some of the measurement methods require a map, a pre-processing, or multiple measurements. The paper contains further links to publications with more details about the measurement methods. We present here in total 22 measurement methods that are split in these 3 categories. The first sensor type is the Global Navigation Satellite System. A GNSS receiver measures pseudo-range, Doppler, and carrier phase measurements to multiple satellites in view. A GNSS can be used to process the train speed from Doppler or time difference carrier measurements. The speed can be integrated to relative distances. The train length can be measured with 2 GNSS receivers, a map, and a relative train localization method. A second way computes a baseline between 2 GNSS receivers with a double difference method. This baseline is the direct distance between 2 receivers. GNSS is also very suitable to determine the absolute along track position and to identify the track at the switch. The first way uses position solution and the map. The second way computes the train location with pseudo-range measurements to satellites and the map. The second type of sensors is the IMU, the inertial measurement unit. An IMU measures accelerations and turn rates in 3 different axes. I will show 3 different ways to use an IMU. The classical way is a processing in an inertial navigation system, an INS, in combination with GNSS measurements. You can see the attitude of the train with bank slope and yaw angle of several train runs. Another way is called kinematics of the track geometry. Turn rates and accelerations can be measured on a running train in curves. There is no integration required. You can see the bank slope and yaw curvature from several train runs. The third way measures the characteristic vibration intensity. All these signatures are called inertial signatures. This picture shows a selection of inertial signatures and a compact regional train. The train speed can be measured in various ways. The first way uses a long track acceleration and it is integrated twice for relative distance. The second way computes a velocity from known and speed-dependent signal patterns. The third way computes a speed from 2 different sensors with a known distance and measures the time via correlation and the shift between the 2 vibration signatures. An IMU can be used for relative measurements on track. There, the correlation shift of the inertial signature is evaluated between 2 sensors. An IMU contributes also to absolute train localization, especially in the track identification at switches. An along track position can be determined with the inertial signatures. The third type of sensor is the magnetometer. It measures the magnetic field density in Tesla in 3 axes X, Y, and Z. The sensor elements are also used in an electronic compass, for example. Our sensor can be seen on the right picture. A railway environment, shown in this picture, creates a characteristic distortion of the magnetic earth field. You can see here many materials made out of steel, which is a ferromagnetic material. This is now an example of a train run over 700 meters. The signal shown on this graph is called magnetic signature. The signature can be measured with magnetometers inside or outside of the train. The train runs now a second time over the same tracks, and you can see now the green signature matches exactly the red signature. The train runs now a third time over the same tracks, and you can see now a blue signature matching exactly the two others. This shows an excellent repeatability and signal-to-noise ratio. This is now the switch scenario. Before the switch, the train runs 6 times over the single track, and after the switch, the train turns out 3 times, as seen in the orange signal, and 3 times straight. This can be used for the identification of the switchway, and there is an excellent separation for parallel tracks. The magnetic signatures are also present in tunnels. You can see here 5 times the signature of a tunnel. Let's come to the magnetic measurement methods. We can see here 2 magnetometers on a compact regional train and the magnetic signature. The train speed can be measured with an evaluation of periodic signals from the rotating steel wheel. The other ways are similar to the IMU speed methods. A speed can be determined from known and speed-dependent signal patterns. Finally, the train speed is determined from 2 sensors that are mounted with a known distance and a time shift evaluation of the 2 measured signatures. The relative localization is achieved with the correlation shift of the magnetic signatures at the same time. The magnetic signature is very suitable for absolute localization. The along track, the switchway and the parallel track can be identified with the magnetic signature measurements and the map. Finally, one approach has been shown with an INS that is aided from position updates that come from a map and magnetic signatures. The fourth sensor is the terrestrial radio ranging. Radio ranging systems measure mainly ranges via round-trip delay and sometimes Doppler. The train speed can be determined with the Doppler from the train to base stations of a cellular network. The relative train localization can be achieved with direct radio ranging on trains. Another way is to process the train length with a propagation difference of a base station signal that is received at the train front and the train end. In terms of absolute train localization, with enough base stations in the vicinity, a cellular positioning computes a position from multiple ranges of the different base stations. The train location is then processed with a map. Alternatively, the measured ranges can be processed directly from a track map in a tightly coupled approach for the absolute train localization. This work showed measurement methods from GNSS, IMU, magnetometer and terrestrial radio ranging. The current and future research focuses on localization algorithms based on a digital track map with INS, GNSS, inertial magnetic signatures for reliable train speed, train location and train integrity monitoring with highest availability in all environments. Further, the research focuses also on safe train localization with navigation integrity methods for railway with advanced sensor models. I hope you enjoyed this talk. You can ask me questions at the Q&A session. Please have a look also at the paper. If you're interested in more of our work, all our publications and links to publications are on our electronic library, elib.dlr.de. My name is Heirich and I'm looking forward to your questions.